system, which costs $11 million for a server farm, will cost only $1 million, only one rack. And this one will spend 30 kilowatt, this one will spend 28 kilowatts. So the advantage, and this is by the, if we use the NVIDIA Tensor Core GPU, if we improve it by 20, you can see that is a significant reduction in cost and really great performance. So this is the way to go. And the way to go, and this I took from the, again, this is a TSMC slide by the last IEEE conference. And this is a 193 excimer laser immersion lithography. And this is the EUV lithography. And you can see how sharp are the lines. And this is, there's no scaling here, but this is a technology that people will use for the 5 and 3 nanometer technology. So new materials is the problem, how to monitor ultra thin layers, how to do surface cover, thickness, composition, defects monitoring, maybe using other semiconductors, but still silicon somehow it's always coming the winner. So I will skip this slide. In the back end, we talk about gate delay. If you talk about gate delay in the back end, you see gate delay, the red line is the interconnect delay in picosecond, and the blue line is the gate delay. And you can see that already in about 2004, the red line, which is the gate interconnect delay, become the big problems. I took it from YOL report 2007. So the main limit for speed today is the interconnect. And if I took this interconnect sketch, I took it from an IBM slide presentation recently, and this was a 1, 2, 3, 4, 5 metallization layer. In 2002, we switched to the 6th, and they have the blue global interconnect. In 2004, we have 1, 2, 3, 4, 5, 6, 7, 8 interconnect layer. 2006, it was 1, 2, 3, 4, 5, 6, 7, 8, and 9 layers. In the 2010, they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 layers. And green interconnects, yellow, each one has a purpose, each one is a different design. And if we talk about less than 10 nanometer metallization, we also need to have ultra thin barriers, which technology to put it, which conducting materials. So there's a lot of material science also involved. So this, one of the solutions is to go to 3-dimensional integration. I will skip this slide. I would like to go to, I would want to go to this slide. In a 3D integration, the most obvious design, which was presented in 2009, is to have the CPU on one layer, on one wafer, your memory in a different wafer, and we can pack them together on a package. And the package is kind of connecting, also helping the connection between the CPU and the memory. The advantage of this approach is you produce the CPU separately, you advance the memory separately, and you package them separately. So you can pick up the best CPU chips, the best memory chips, and then to package them. So you improve your yield. The problem is that you add some extra step of packaging, but this is the way to go because you can put more bits per unit area. Another way to do is why not do optical interconnects. And optical interconnect, for example, is doing wavelength dispersion modulation. You put a waveguide on your chip, you feed the information in one part, and you send the information to the second part. You put here some sensors and circuits. And this was published 2004, and you can see the reason I'm showing it today, this was known for many, many years, but still under development. There are still a problem here because silicon is not a good material to generate light. Actually, you cannot generate light using silicon. And also silicon is not such a good sensor for infrared for near infrared, which is typically the light that people use in these optical waveguides. So you need, if you want to do on-chip optical systems, you need to integrate other semiconductors. So silicon, so it's a technology issue, but optical interconnect is a very intriguing concept. Currently, people use copper metallization, maybe carbon nanotubes people are talking about, and 3D integration. I'll skip this slide. One direction in future VLSI design is a multi-core design, including integrating a lot of cores on the chip. You are reducing the critical path, they improve there's some mechanical integrity challenge, some hierarchical structure maybe no longer be necessary. You have the global delay challenge, a 3D challenge, and there are some issues. One way, some tricky issue to reduce the capacitance, why not using air? Instead of putting glass, we put, this is a metal line. I'm sorry. This is a metal line, M1, and between the metal lines, you put some air, so you reduce the capacitance between the lines. So technology, again, is a driver for improvement. So if we summarize this talk, I'm going to have a few more slides more. If you look at the bandwidth deficit that limit the system throughput, this is 2006, and this is 2020, which is today. Normalized bandwidth is increasing by a factor of about 1.6 every 2 years. If we normalize throughputs, we can increase it, but still, we still see an increase. If you look at this, it's still under, this is a log scale. I told you, if you want to look at Moore's law, you plot your variable in the log scale, in the year, in the linear scale, and we still see a kind of, we still see a growth of 1.6 times every 2 years. So Moore's law somehow is still going, even though we reached the limit. So now, can we look at some completely different VLSI approach? Maybe biocomputing and synthetic biology. For example, just maybe we have to think about computer system. If you think about this, I took from a paper that published. If you look at the cell, and in a cell you have DNA, and we can have logic proteins, sensor proteins, communication, signaling molecules. Why not using biological components or carbon components for computing? For example, protein molecules formed from different amino acids, so we can have this molecule to store some information, or using a DNA molecules on the backbone. This is 0.34 nanometers. This is adenine, thymine, guanine. So this is, we have 4 variables, so we can store much more information using DNA as an option to store information. So why not making DNA-based storage? And if you look, for example, let's compare bacteria, E. coli, or this marinus, or protozoa, amoeba, or human cells. This is the volume. And the genome side, our genome is about 6 gigabit. And the bacteria is about 9.6 megabit. Let's make this calculation, and let's compare our devices. If we take a DNA size of 9.6 megabit, and this is, we look at it as a non-volatile memory. And the number of RNA per cell is about, this is the memory interface. Remember, RNA is transferring the information from the DNA to the machine. So we have the memory interface of 222,000 bits. Number of cytoplasmic proteins are about 1 million. We can look at them as logic processor, signal processor, and metabolic functions. Ribosomal protein is also close to 1 million. This is our interface because the ribosome is translating the information into proteins. Number of logic devices is 1 million. Number of all proteins about 3.6 million. Time of cell replication is 40 minutes. And what is the energetics? The number of glucose molecules per cell is about in a few hundred thousands. Number of ATP, adenosine triphosphate per cell. This is the energy, the phosphate for transfer the energy, about 500,000 to 3 million. Total energy stored is 2 picojoule. So the power dissipation is about 1.4 to 10 to the minus 3 watts. So if you compare computers to cells, in cells, the memory is 10 to the 7 bit. In computers, the memory is about, in single silicon, even in the best operation, multi-cell, vertical, we can store like 1,000 bits or maybe 2,000 bits, 10,000 bits. The logic, we can have this number. The power is 10 to the minus 7. The heat is about 1 watt per centimeter square. However, the task time in cells is take 40 minutes. And if you want to do the same task in silicon, it will take much, much longer. And this is, I'm doing the calculation for 10 to 11 output bits. So if you think about the throughput of a biocell, it's much, much better. The problem is that the biocell, we cannot run Excel, we cannot do Office, we cannot play games. It's a different type of computing. But I'm comparing these two computing machines, and I'm doing this computing. If I want to generate 10 to 11 output bits, in a biocell, it will take 40 minutes. In silicon, it will take 66 days. So if you want to do biological computing, biological system, of course, cell is much better than silicon. If you want to play games or to read your email, silicon is much better. So what is the future? Still, the future is a system integration, and there are 4 factors. One is more transistors, 2D shrink, DTCO, and 3D integration. More memory, vertical integration, and dense 3D connectivity. More logic memory integration. We have chiplets, active on monolithic devices, and end-to-end optimization. So the simulation or the modeling, we need more software to go end-to-end simulation from the transistor to the full thermal management. So industry roadmap, what is the future? Energy efficient performance. Until 2012, we use what we call equivalent scaling, high K metal gate or strained silicon. Today, we use FinFETs, enhanced UV, extreme UV lithography, high mobility devices, and DTCO concept. So where shall we go? We hope that we keep going 2040 and go, we'll design 100 times better performance system. This is a wishful thinking. And with this slide, and this is the end of my talk. I think I'll go back to this slide. This is kind of a summary of my talk. This is the industry roadmap. I took it from TSMC. This is presented recently. And this is a very optimistic slide. Hopefully you guys and my students and your students will be able to deliver this technology. Okay, so this is it. And now I'll switch. I think I'll stop sharing. And you can see me now in my office. I'll go back a little bit. And if you want to have questions. Oh, we grew up to 91 students, which is amazing. Thank you so much. It's really very good turnout, sorry. And we are now open to questions. If anybody has questions, we promised to have this lecture about up to 1.5 hours. So I kept about 10-15 minutes for question and answers. You're free to ask. Microphones are open. Raise your hand or just talk directly.
It is possible to
introduce yourself first.
I am Vazgen Melikan from Armenia.
Okay.
What do you think? What is the perspective of 3 nanometer GAA technology in sense of manufacturing?
I think it's possible. I think it's possible. For manufacturing, it's possible. The big unknown will be the yield and the cost and the profitability. But as I showed you some already, they already have prototypes and